Folks, this lesson is going to be on sequences. We're going to start off by differentiating between the two main types of sequences that we're going to learn about in this course. This should have been something that you learned in Algebra 2 or Algebra 2 Trig, but this will be a nice review if you don't remember this. So the two main types of sequences are arithmetic sequences and geometric sequences. In an arithmetic sequence, the list of numbers will have a pattern, and that pattern will always be either adding or subtracting. And arithmetic sequences are really similar to linear functions, right? So like when you graph an arithmetic sequence, it makes kind of like a straight line. And so down below here we have two arithmetic sequences, and we're just going to practice finding the pattern of change. So for this first sequence on the left here, 4, 7, 10, 13, we can see that the pattern of change is adding 3 because 4 plus 3 is 7, and 7 plus 3 is 10, and 10 plus 3 is 13. So that means that our pattern of change would be plus 3. For this second sequence, we can see that the pattern of change is going to be minus 7. Because 56 minus 7 is 49, and 49 minus 7 is 42. Okay, so if an arithmetic sequence is adding and subtracting, a geometric sequence is going to be multiplying and dividing. So for that reason, geometric sequences end up being very similar to exponential functions. And so you can see here we have two examples of geometric sequences. The first sequence, 15, 45, 135, 405. You can see that 15 times 3 is 45, and then 45 times 3 is 135, and 135 times 3 is 405. For the next sequence, we can see it's getting smaller, so we say that this one has decay. The first one had growth that we looked at. So 200 to 50, we're dividing in this one. In this case, we're dividing by 4. And then, again, we're dividing by 4 to get from 50 to 12.5. Okay, so those are our two main types of sequences. What we're going to talk about next is how we can write them as formulas. We sometimes call this sequence notation. Okay, so for an arithmetic sequence, and we're going to talk about two different types of formulas that we can write for our sequences, so recursive and explicit formulas. So for an arithmetic sequence in the recursive form, we're always going to be starting, so we write this as Tn equals Tn minus 1 plus C. So you can see that all of our formulas, whether they're arithmetic or geometric or recursive or explicit, they're all starting with T of n. So T stands for term, and n tells us which term we're looking at. So if we were looking for T1, that would tell us the first term of the sequence. If we were looking for T100, that would tell us the 100th term of the sequence, so like the 100th number in the list. Sometimes a lot of formulas will use AN instead of TN, but that doesn't really change the problem at all. It's still essentially the same formula. Okay, so whenever we're looking at a recursive formula, we're always looking at the previous term and then applying the pattern of change. Basically what this formula is telling us is that if we know a term in the sequence and we know the pattern of change, we can get the next term by applying that pattern of change, right? And if it's arithmetic, we're always going to be adding. You could also think of it as subtracting or adding a negative number, but we are applying that pattern of change to get to the next number. Okay, in an explicit formula, again, we're starting with t to the n, but now there's no t to the n minus 1 in this formula, right? Instead, we still have c, but we, instead of t to the n minus 1, we have n and t0. Okay, so what do those terms mean? Well, again, n is which term of the sequence you're on. So, for example, if we're looking for t11, we would put in 11 for n, because that means that we're looking for the 11th term. C is still the pattern of change, and t0 is the starting term of the sequence. Now, this can be a little bit confusing because usually we'll think of the starting term as the first term. For all extensive purposes, the starting term will actually be t0, so it'll be the 0th term, so the term that kind of like comes before the starting term. I think this will make more sense once we look at some examples. You can kind of think about, remember that arithmetic sequences are similar to linear functions. This is like the same thing as the y-intercept. The starting term in the is very similar to the y-intercept. Okay, for our geometric sequence, as we look at our recursive formula, we can see again we have t to the n minus 1, and that again represents the previous term. So like if we know what the 4th term is, we can figure out the 5th term by applying the pattern of change. Unlike with a recursive formula, instead of adding or subtracting, we're going to be multiplying or dividing. So we're going to multiply by our rate of change. And again, t to the n minus 1 is just the previous term. Okay, and so then last up, our explicit formula for a geometric sequence is going to look like this. Right, so again, we have that t0, and that represents our starting term. R still represents the rate of change. Oh, I hope you can see that. Looks like that's blocking it here. Let me close that. There we go. R represents the rate of change. And then n represents which term you're on. So if you want to find out the 23rd term of the sequence, we'll plug in 23 for n. Okay, let's go through a few examples here. In each of these examples, we're going to write the recursive and explicit formulas for the sequence, and then we will kind of solve the problem that they ask us to solve on there. Sometimes it'll be evaluating, sometimes it'll be solving for n. Okay, and then you can see for each one I wrote a table out. You don't actually have to write out the table, but I think for a lot of you it'll be helpful in writing the formulas. Okay, so let's do this first sequence, 4, 7, 10, 13. We kind of saw that one on the other page. And you can see that I filled it in here, 4, 7, 10, 13. These are the values of t to the n. I also filled in the n values up here. So 4 is the first term of our sequence, 7 is the second term, 10 is the third, 13 is the 4th term. I also put a 0 up there, even though we don't actually know what the 0th term is yet. We'll need that when we write our explicit formula, so I'm just leaving that blank for now. Okay, the first thing we should try and do is figure out our pattern of change. We already did that on a previous slide. We saw that it was all plus 3. Right, adding by 3 each time as we go up. So what does that mean for our recursive formula? Well, our recursive formula is t to the n minus 1, so that's the previous term, plus 3. So for example, since I knew that the 3rd term was 10, I can figure out that the 4th term is 13 by simply adding 3. That's all the recursive formula means, is what do I do with the previous term to get to the next term? That should be pretty straightforward. Now let's start to figure out the explicit formula. To do our explicit formula, we first need to figure out what our 0th term is. And so in order to do that, we need to go backwards from our first term. If our first term is if our first term is 4, right, and we're adding by 3, then we need to subtract 3 from 4 to get our 0th term. 4 minus 3 is 1. And so then our formula, our explicit formula is going to become 3 times n plus 1. Let's just check and see if that works. Will that get us to our third term? If I take 3 and I plug that in for n, 3 times 3 is 9, plus 1 is 10. Appears to be working. Okay, and then the last thing we're going to do is solve this problem. They said, then find the 12th term. So we're going to say t 12, so I'm putting in 12 for n here, equals 3 times 12 plus 1. Again, I'm putting in for n 12. 3 times 12 is 36, plus 1 is 37. So that would be the answer to what the 12th term is. T12 equals 37. All right, let's do example 2. So we've got our sequence written up here. You should be able to see pretty quickly that this sequence is geometric. We can tell that it's geometric because we're multiplying. Like the numbers are getting really big really quickly. We saw earlier that we were multiplying by 3, right? 15 times 3 is 45. All right, so then we can write our recursive formula. We're just taking 3, and we're saying 3 times our previous term. That's what Tn minus 1 is. Will get us to the next term. So I knew that my second term was 45. 45 times 3 is 135. That's how the recursive formula works. Explicit formula should be a little bit simpler. Okay, so for the explicit formula, we're starting with our starting value. So again, to do that, we have to go backwards. So instead of times 3, we're going to do divided by 3. 15 divided by 3 is 5. So we're starting off with 5. And then we're going to take that times our pattern of change, which is 3. Whoops. And then that's raised to the n power. Okay, next we're going to try to find the 9th term of our sequence. Now, I should mention, like, and this works with the last problem too, you could just extend your table out to 12 to get the 12th term. Same thing here. We could just extend the table out to 9 to get the 9th term. You can imagine you wouldn't want to do that if I was looking for the 1007th term, right? At that point, it's going to be much more simple if you use the explicit formula to find the value of that term. So in this one, we're looking for the 9th term. So we're taking 5 times 3 to the 9th power. So then T9 would equal 98,415. Okay, in example 3, we're again going to find the recursive and explicit formulas. This time, though, they're asking us to solve for n. So instead of looking for a specific term, they're asking us which term is going to be negative 145. And so for this one, again, I would say that it's going to be much easier to use the explicit formula than it is to extend the table, although you could theoretically do that if you wanted to. Okay, so for this one, remember we're subtracting by 7. 9 minus 7 is 2, minus 7 is negative 5, minus 7 is negative 12. Okay, so that's our pattern of change. This is arithmetic, so we're taking t to the n minus 1, and then we're subtracting 7. T to the n minus 1 minus 7. Okay, so now we're going to go backwards and get our 0 term. So instead of minusing 7, we're adding 7. That gets us to 16. So our formula is going to be negative 7 times n. So negative 7 is our pattern of change, and then plus 16, because that's our 0 term. And now we're going to use that to figure out which term is going to equal negative 145. So now instead of plugging our number in for n, we're going to plug it in for t to the n. And so we'll say negative 145 equals negative 7n plus 16. We're going to solve this, we'll subtract 16 from both sides. That will get us negative 161 equals negative 7n. Then we're going to divide by negative 7 on both sides. 23 equals n. Okay, last up, this one is going to be similar to example 3, except it's going to be geometric instead of arithmetic. Okay, so we've got our series. We can see that this one is going down rather quickly, so it's going to be geometric. And recall that for this problem we were dividing by 4. Okay, so then our recursive formula. We could say that this is t to the n minus 1, right? So the previous term, and then divided by 4. I'm going to encourage you to write this with a fraction instead. So instead of dividing by 4, we're going to say times 1/4. The reason for that being is that gives us the decay rate that we're going to use to write our decay rate that we're going to use to write our explicit formula. Okay. And so if we're dividing 4 going forward, that means we're multiplying by 4 going backwards. When we multiply 5,120 by 4, we get 20,480. And so then our formula is going to become 20,480 times 1/4 to the nth power. Right? So notice the similarity between examples 2 and 3. In example 2, our rate of change was 3 because we were multiplying by 3. In example 4, our rate of change was 1/4 because we were dividing by 4 as we went forward. Okay, and then last up, we are going to try to solve for which term is 5. Now, this is one where I would say extending the table might be easier than doing this algebraically. Right? If we divide 80 by 4, we'd be at 20, so that's the 5th term. Divide by 4 one more time, we're at 5, so that would be the 6th term. I'm going to show how to solve it algebraically because you are eventually going to need to know how to do this, especially in trimesters 2 and 3. This should be a review from the exponents and logarithms unit when you were in Algebra 2 or Algebra 2 Trig, and also you would have learned this when you were doing geometric series. Our formula is 5 equals 20,480 times 1/4 to the n power. We're going to try to solve that for n. So the first thing we would actually do is divide both sides by 20,480. You would probably get a fraction if you did this on your calculator. If you use Desmos, it lets you turn that decimal into a fraction. And so your fraction would end up being 1 over 4,096, which equals 1/4 to the nth power. Okay, and then we're going to rewrite that as a logarithm. So I'm going to say the log of base 1/4. So notice 1/4 is the base of my exponent. It's also the base of my logarithm. Log base 1/4 of 1 over 4,096. Put all that in parentheses, equals n. You can take this expression right here and plug that into Desmos directly. If you have a keyboard, you can type the word in. You can type the word log in, and then use shift negative sign to get the 1/4 down in the subscript down there. You could also go in through the functions menu if you're using the graphing calculator and look for the logarithm that way. I believe it's in the calculus section. Okay, and so then when you plug that into Desmos, what you should end up with is 6. 6 equals n, and that's what we said it was when we extend the table as well. Okay, so hopefully this gives you a good review on sequences. If you have any questions, please let me know.